This is the second lecture on Text Unit 6, which concerns atoms and their electrons. Here we'll apply some of the stuff we learned about electromagnetic radiation in the next lecture and study the Bohr theory of the hydrogen atom. It's an observed property of hydrogen atoms that they only absorb and emit radiation at certain wavelengths. This occurs naturally in space. Hydrogen atoms are found naturally occurring in space, in our star, and in interstellar space. So one place that these wavelengths were observed was in astronomy, where hydrogen atoms emit radiation. And also there are laboratory experiments where you take H2, break it down into hydrogen atoms, and chemists have seen that hydrogen atoms absorb that radiation as well. While the radiation is getting absorbed or emitted, it obeys the Rydberg formula, which we have down here. Okay, notice on the left-hand side we have the reciprocal of the wavelength. On the right-hand side we have the Rydberg constant, which notice is in reciprocal meters. And then in braces we have 1 over n1 squared, 1 over n2 squared. N1 and N2 are a pair of numbers, 1, 2 natural numbers, 1, 2, 3, 4, etc. So you can, in principle, find one of the wavelengths at which hydrogen emits or absorbs by picking any pair of natural numbers and sticking them in the formula. Now, to avoid getting a negative number, you should always pick N2 greater than N1. Okay, so that's how the formula works. Here's an illustration. So suppose n is 1, n1 is 1, is n2 is 2. Like I say, just pick 1 and 2. Make n sub 2 2 because we want that number to be greater. Right? Then 1 over lambda is r times 1 over 1 squared minus 1 over 2 squared, which is r times 1 minus 1/4, or r times 3/4, 0.75. And then I insert the value for r, 1.097 times 10 to the 7 meters times 0.75, and I get 8.228 times 10 to the 6 reciprocal meters. Now I've highlighted this 0.75 in red because this 1, this 2, this 1, this 1/4, and therefore this 0.75 are all exact numbers. And my solution has 4 significant figures. Except, well, this number has 4 significant figures, I should say, because this is not the solution. Notice the units. It's in reciprocal meters. What we wanted was a wavelength in meters. What we've solved for is 1 over the wavelength. To get the wavelength, we take the reciprocal, which is the same as dividing by 1, and this number is 1.215 times 10 to the negative 7 meters. Alright, now a helpful exercise for you at this point should be to calculate and write down somewhere nearby the frequency and photon energy that corresponds to this wavelength. And now in principle, numbers of wavelengths for hydrogen atoms can get calculated from this formula. Alright, for review, given a wavelength, you can always find a frequency and an energy. So the frequency you should have calculated is found by taking c and dividing by the wavelength we just found. 3 times 10 to the 8th divided by 1.215 times 10 to the negative 7. Meters cancel. Our frequency is 2.47 times 10 to the 15th. Reciprocal seconds are hertz. And we can calculate an energy by multiplying that frequency by the Planck constant. Notice seconds cancel, and our solution is 1.64 times 10 to the negative 18 joules. All right, moving on. Rydberg formula can be viewed as a law in terms of our discussion and in the scientific method at the beginning of the course. Excuse me. Naturally, scientists all also wanted to have an explanation for what was going on in hydrogen atoms. It says, why does this absorption and emission of radiation of certain wavelengths occur? And the theory that explained it first is the Bohr model, and of the hydrogen atom, and I've more or less made a picture of the Bohr model here. We have the nucleus for the atom, and electrons that orbit the atom are compelled to occupy certain orbits. In other words, they could occupy orbit 1 or orbit 2 or orbit 3, but could not, for example, be at a distance between 1 and 2. Notice that as you increase the number, the energy, the number of the orbit, the energy goes up. The energy is defined as a negative number, negative b over n squared. So the bigger the n, the smaller the energy, in fact. And the largest possible least negative energy will be 0 when n is infinity. Distance from nucleus also increases as n goes up. Right, so you have these states or orbits that are allowed. Now it's possible, well, in the cartoon we show the electron jumping from 3 to 2, in which case the energy goes down and a photon is emitted. Likewise, if you are in n equals 2 and jump down to n equals 1, a photon will be emitted. And the energy of the photon, h nu, will be equal to the change in energy of the atom. So for example, if you jump from here to here, the change in energy of the atom is the energy of the photon that leaves. Similarly, if you're in 1 and jump to 2, well, you have to put energy in the form of a photon, and the energy of the photon is equal to the energy you put in. So I write down here, change in energy of the atom is equal to h nu, where this is the frequency of the photon involved, absorbed or emitted. Now Bohr's theory determined that the value of B is 2.18 times 10 to the negative 18 joules. Alright, now suppose n equals 2 goes to n equals 1, or vice versa, 1 goes to 2. What is the energy and frequency of the photon emitted or absorbed and vice versa if 1 is going to 2? The change in energy, remember we use these deltas for change, is the energy of 2 minus the energy of 1. Now I write down that change this way. I put 2 first, regardless of whether we're going up or down in energy, because I want to get a positive number. All right. This is equal to negative b over 4 minus negative b over 1 is equal to b times 1 minus 1/4. Which is b times 0.75. Now I've turned this 0.75 red again because this is an exact number. Multiply that by the Bohr constant, and I have the energy change for jumping from 1 to 2. I get 1.648 times 10 to the negative 18 joules. Now at this point, you should solve for the frequency and wavelength that correspond to this energy before going on in the presentation. Alright, frequency, as usual, is found by taking the energy of the photon. We just calculated the energy of the photon. Divide that by the Planck constant, which we know from the last lecture. 1.64 times 10 to the negative 18 joules gets divided by 6.626 times 10 to the negative 34 joules times second. The units that survive are reciprocal seconds, and we have 2.48 times 10 to the 15th reciprocal seconds. Once we have a frequency, we can solve for the wavelength. Lambda is c over nu. This frequency goes in the denominator. Speed of light we remember. When we calculate the wavelength, seconds cancel, and the units are 1.21 times 10 to the negative 7 meters. Alright. Compare these values to the wavelength, frequency, and energy from the Rydberg formula for numbers 1 and 2, for the calculation we've done before. And you will see that Bohr's theory matches or predicts experiment, or what you would get from experiment as shown by the Rydberg equation. Or Bohr predicts the Rydberg theory. Or, I'm sorry, Bohr theory predicts the Rydberg formula. That's one way to say it. Now you should try this, again, with any pair of numbers. Pick any pair of numbers like 1 and 3, and repeat both exercises, the Bohr formula and the Rydberg formula. And you'll see the theory and that the law and the theory give the same numbers. So it seems, well, at least at this point, from what we've talked about here, like the Bohr theory is a successful theory for describing atoms. We'll have more on that in the next lecture. This ends the second lecture for Unit 6.